LHS 1903 may be the kind of planetary system that quietly breaks your confidence in how worlds are supposed to form. Not inner rock, not outer gas, but a likely rocky outer planet that seems to have arrived after the neat order was already gone. That is the unsettling part. The title suggests a strange system. The deeper problem is worse. If this interpretation holds, at least one planet in LHS 1903 may have formed in a different environment, at a different time, with a different script. And if that can happen, our solar system may be less like a universal blueprint and more like a lucky local habit. In 2026, researchers studying the compact LHS 1903 system pointed to a pattern that feels almost wrong on sight. Inner rocky worlds, then a gaseous middle planet, then an outer planet that appears rocky again. That inversion matters because planets usually inherit the temperature structure of the disk that made them. Hotter close in, colder farther out. Rock inside, volatile rich bodies farther away. Think of a bakery oven. The tray closest to the heat browns first. The far side stays cooler and wetter. Planetary disks are not that simple, but the logic rhymes. You expect materials to condense in zones. Iron and silicates survive in hotter regions. Ices and gas-rich growth become easier farther out. So what is LHS 1903? It is a red dwarf system around a small, cool star with multiple planets packed relatively close compared with our own giant spread from Mercury to Neptune. Around stars like this, astronomers often find compact systems that already challenge our instincts. But LHS 1903 adds a sharper insult. It may not just be compact, it may be inside out. And that takes us to the real question. Did the system form in the wrong order? Or did it form in a normal order and then get rearranged so violently that the final architecture only looks backward? Oh, astronomers usually infer a planet's nature from size, mass, density, and orbit. A rocky planet is dense, more like compressed stone and metal. A gaseous or volatile-rich planet is puffier, with lower density for its size. In transiting systems, if you get a radius from the dip in starlight and a mass from the star's wobble, you can estimate bulk composition. It is not like reading a label on a can. It is more like weighing a sealed suitcase and guessing whether it is full of books or winter coats. That is where systems like this become forensic science. A radius near the so-called Fulton gap can already hint at whether a planet held on to an atmosphere. The gap itself was mapped in 2017 by Benjamin Fulton and colleagues using California Kepler survey data, showing a shortage of planets around roughly 1.5 to 2 Earth radii. On one side sit super-Earths, often rocky. On the other sit sub-Neptunes, wrapped in gas. If LHS 1903 really places a denser rocky world outside a puffier middle planet, that is not just weird. It implies either migration, atmospheric stripping, delayed formation, or some combination ugly enough to erase the clean classroom version of planet formation. And personally, this is the part I cannot shake. We like cosmic order. We like the idea that nature stacks its shelves logically. Rocks here, gas there, ice farther out. LHS 1903 suggests the shelves may have been knocked over while the store was still open. Before I show you the two main explanations, which feels more convincing to you already? a late-born outer rocky world, or a migrated planet stripped down later? Tell me which one and why. Explanation 1 is migration. A planet does not have to stay where it forms. Young planets move through the gas disk like boats drifting in a current. Some spiral inward, some get caught in resonances, some scatter each other into new lanes. We have seen enough exoplanet systems to know that calm textbook order is not guaranteed. A famous clue came long before this system. In 1995, Michel Mayor and Didier Queloz announced 51 Pegasi b, a giant planet orbiting absurdly close to its star in just about 4.2 days. That discovery forced astronomers to accept that planets can travel far from their birthplaces. Since then, migration has become less a special excuse and more a standard ingredient. In that picture, the outer, rocky-looking world in LHS 1903 may not have formed there at all. It could have started farther in, or the middle gaseous planet could have moved, reshuffling the system like furniture dragged across a wooden floor. But there is a problem. Migration explains position. It does not automatically explain composition. To leave a rocky world outside a gaseous one, the dance must preserve a very specific final pattern. Explanation 2 is harsher, and to me, more existential. The outer rocky world may actually be younger. Not young in the sense of newly glowing lava under a telescope. Young in the sense that the solid body we see could have assembled later, after the original disk environment changed. Maybe from collisions. Maybe from stripped cores. Maybe from material that gathered after the easier gas-grabbing era had already ended. That would mean some planets are not just born in different places, they are born in different eras. Picture a city built after the highway system was already finished. The downtown towers went up first, the suburbs spread next. Then, years later, somebody built a dense stone fortress beyond the ring road, using debris from earlier construction. It would still be part of the same city, but it would not belong to the same phase of planning. That is what makes this idea so unnerving. Astronomers have reasons to take delayed outcomes seriously. Planet formation models have long shown that core growth, migration, atmospheric loss, and giant impacts can overlap. In 2005, work by Alessandro Morbidelli and colleagues on giant planet migration helped cement how dramatically orbits can change. In 2012, studies of atmospheric escape around close-in planets showed that stars can strip lighter envelopes away over time. And by the 2020s, JWST began adding better atmospheric constraints on some sub-Neptunes, reminding us that classifying a planet is often a moving target. So when a system like LHS 1903 appears to go rock, gas, rock from inside to outside, it presses on a dangerous idea. Maybe planetary systems are not products of one clean assembly line. Maybe they are patchworks. Some worlds born early, some transformed later, some rebuilt from damage. The system may not merely be out of order. It may be exposing a blind spot in how we define a planet's identity in the first place. A rocky planet is not a birth certificate. It is a current condition. If a planet loses a thick atmosphere, collides, gets baked, or is partially stripped, the object we classify today may be the survivor of several earlier versions. Like cannon recoil in space, the final motion makes sense only if you remember the push that happened before you looked. So the outer world in LHS 1903 may be rocky now without being born rocky in that orbit. Or it may truly have formed late from leftover solid material. Those are very different histories that end with a similar-looking planet. That is the forensic trap. Tense. This is why more data matters.
Better mass estimates, better radius measurements, better stellar age constraints, maybe even atmospheric clues if the geometry and instruments cooperate. A tiny change in density can flip the story. The difference between an iron-rich super-Earth and a volatile stripped remnant can be the difference between train tracks and ash in a furnace. Iron means bridges, blood, frying pans. In a planet, it means a denser interior and a very different past. If this reversal is hitting you the way it hit me, leave a like. Because a system that may have built a rocky planet last is exactly the kind of clue that changes how we read every other planetary map. My view is that the deeper importance of LHS 1903 is not whether one specific outer planet is definitely late-born. The deeper importance is that the system makes that idea scientifically reasonable. And once that door opens, neat categories start leaking. Habitability becomes harder to judge. System history matters as much as present location. A rocky planet in the so-called right zone may be a stripped corpse. A gaseous planet may hide a dense core with a violent past. An outer rocky world may be less a quiet leftover and more a monument to chaos. Can you imagine trying to reconstruct Earth from a single snapshot taken 4 billion years from now? Continents shifted, oceans changed, atmosphere transformed. Now apply that blindness to another star system tens of light years away. We're not looking at childhood photos. We are looking at survivors. And personally, I find that beautiful in a slightly unsettling way. The universe may not build worlds as a neat sequence from hot to cold, inner to outer, simple to complex. It may improvise. It may revise. It may build a late stone world after the gas age is already over, the way a thermos left in a blizzard keeps one small pocket of warmth long after the room has gone cold. That is the payoff. LHS 1903 is not compelling because it is weird. It is compelling because it threatens a comfort. The comfort is that planetary systems should make intuitive sense. The evidence coming from exoplanets keeps saying otherwise. So maybe the real discovery of 2026 is not a bizarre planet. Maybe it is the possibility that order itself was the anomaly we projected outward. Maybe our solar system is not the template. Maybe it is the exception that made us overconfident. If that kind of cosmic inversion fascinates you, subscribe. This channel is for people who want the universe to feel bigger, stranger, and a little less obedient every week.